I am doing well. Thank you for asking. It's been a crazy couple weeks.
That's the first try. That's fun.
That's because I just logged out and logged back in.
Oh,
I kind of thought I better nip this one in the bud today and make just leave and come back in and see if it works. Um, yeah. So how have you been staying inside, self quarantine?
yep. I haven't seen anyone for 2 weeks now, maybe
Wow.
three weeks.
Do you go outside at all?
Oh yeah.
Okay. All right. I was going to say that would drive me crazy. I mean, my wife and I would take our dog up to the dog park every day to walk
Mm,
around. I go out on the lake. Like yesterday, I went out fishing. Tomorrow it's supposed to be 70, so I'll go out fishing again. And those are
ooh,
all things I can do by myself. So I'm
yeah,
I'm good.
yeah. By seeing people, I don't mean like physically seen, by
Yeah.
like
Okay.
a gathering or a orchestrated time to be with someone.
Yeah.
I have walked past people on the sidewalk and you know,
Yeah. It's now. Did you have a job before this all started?
I did not, but
Okay.
we'll see how it affects summer work, that's for sure.
Yeah. I have a feeling that there's not, like you have a lot of places that, they hire just summer help, like the Dells and stuff like that. I don't think you're going to have as many people traveling this summer as you have in the past because people, when they
Hmm.
get done with this, they're not going to have money, first of all. And then second, who wants to go and sit in a crowd when you don't know if it's all gone? I mean, I,
Right.
I think it's going to be a while before things get back to normal, but we'll see.
Yeah, we certainly will. I hope it ends somewhat soon. I'm sure everyone does.
Yeah, I'm just
Yep.
interested to see how that AP exam goes. I mean, you took the AP exam last
Mhm.
year, correct?
Yes, I did for AB calculus.
Yeah. So now this year with only 45 minutes, I'm gonna definitely ask you your take on it after it's done,
Mm.
because
Mhm.
I have no idea. My assumption is they're probably going to do maybe 10, 15 multiple choice questions and maybe two free response. That is what I would think. But
That would still be pretty time constraining for 45 minutes.
yeah, well, free response questions are always they always give 15 minutes for those. So that would be a half hour and then 15 minutes for or for multiple choice. Yeah, you're not going to, I would say you probably get about 2 to 3 minutes. Yeah,
Yeah,
I don't know. It is
maybe.
going to
Yeah.
be interesting. But
Last year, I only wrote an answer to, I think, 70% of the total questions or so,
yeah. And
but
what
I
did you
still
get on
got,
it?
I did get a 4.
You got a 4? Okay.
Yeah, but
Now,
man, it was hard.
do you know that if you get a 5 this year, they go back and give you a 5 for the AP?
Didn't that sounds good to me? That'd
Yeah.
be awesome.
Yes. I believe so because if let's say you didn't take the AB test and you take the BC test and you get a 5, you automatically get a 5 for the AB test also. So I would assume they'd go back and change the AB test score. That is that is how they've done it in the past. So I would assume they would, but everything's on the table this year. Who knows? I have no clue what they're going to do. All right, let's get going. I'm not sure where what's his name is, Henry, today. This week is only a 4-day week. Okay, so you don't have school on Friday, which is really weird because I mean it's online, so you can do your work anytime. But the big one is there's no school next week, Monday also. So next week there will not be a main lesson. I will record it and put it into the recording. Okay.
Sounds good.
All right. Last week we were talking about P series, I would assume, because these look like P series problems.
Yep.
So, and that was pretty easy, I would assume. There wasn't a whole lot of hard stuff last week. So, if I had to rewrite this problem, I'd rewrite it as 1 over n to the 1/4. And this problem I would write as 12 n to the 0.99 So, do they both converge or both diverge?
They both diverge because P is less than 1.
Correct. Okay, so if P is less than 1, the P series says that it diverges. This week we're going to do a couple comparison tests. Now, um, yeah, there's only a couple comparison tests that they have written down, but I would have a hard time believing they're not going to ask something about the direct comparison and limit comparison. They're very easy to do, so let's take a look at them. The direct comparison test, it says, for the convergence test, the terms of a series have to be fairly simple, and the series must have special characteristics in order for the convergence test to be applied. A slight deviation for these special characters can make a test non-applicable. So for example, when you have a direct comparison test, what you're doing is you're really testing it against another function that is very similar to it, okay? Like 1 over 2n is a geometric sequence. We could find out if this converges or diverges, but n over 2n is not the same thing. So we could not use this as a direct comparison. Now, something like 1 over n to the third is a p-series, but 1 over n to the third plus 1 is not. However, these two are fairly similar to each other, and we could use them to, I wonder if we could use this one too. We'll see. We could use this as a direct comparison. So if we knew that this one converges, we could absolutely find out if this one converges. And that's what the direct convergence test tells us. And this is the rule for direct convergence. It says, if a sub n, if 0 is less than, or if a sub n is greater than 0, and b sub n is greater than a sub n for all n, then the sum from 1 to infinity of b sub n converges, then a sub n converges. Okay, so if we have two functions and we use direct comparison, we can use a direct comparison that says if one of them converges, then the other one converges, as long as this holds true. And if a sub n diverges, so if a sub n diverges, then b sub n diverges. So if if a sub n diverges and all of these values are less than b sub n, then b sub n also diverges. So here's an example. It says determine the convergence or divergence of 1 over 2 plus 3n. So in a problem like this, what I do is I always take a look and I say, okay, I'm going to let a sub n be 1 over 2 plus 3 to the n. And I'm going to let b sub n be 1 over 3n. And then it's like, okay, this is always going to be smaller, isn't it? If you think about it, I believe, because you have 2 on the bottom, and that's always going to be so. So a sub n is less than b sub n. So that is a true statement, and isn't it? Because this is always going to be 2 bigger on the bottom, which makes it bigger or smaller than this one. So then my next step is to figure out, does 1 over 3 of n, is that a convergent or a divergent series? Okay, and this is a geometric series, isn't it? This is 1 over, I could rewrite it as this. So this really is a geometric series. And this is a geometric series that converges, doesn't it? Because my r value is less than 1. So this is a convergent sequence. So that means, and all of these values are smaller than these values. Okay, so these values are always smaller than these values. This function this function converges, so a sub n also converges. Okay, so that is what the direct comparison test tells us, that if we can find a function that relates to it, and we can tell if it converges or diverges, then we can tell if the other one does also. Okay, so that is what we call the direct comparison test. Now there's another test. It's called the limit comparison test, okay, and it's somewhat similar. The limit comparison test says that if you have a function a sub n, which is greater than 0, and b sub n, which is greater than 0, the limit comparison test tells us that if we take the limit as n approaches infinity of a sub n over b sub n, and it equals a number, L, some number, doesn't matter what the number is, where L is a finite and positive number, then either both a sub n and b sub n both converge, or they both diverge. Okay, that is the rule. Okay, this is called the limit comparison test. So let's take a look at an example. Okay. Oh, I thought I erased all that stuff. Okay, it says determine the convergence or divergence of the square root of n over n squared plus 1. All right. So if we take a look, if we let this, all we really are looking at is the highest powers on top and bottom. So I've got n to the 1/2 here. I've got n squared here. So if I rewrite this, what do I end up with? 1 over n to the 3/2. So this is the function that I want to use as, and I don't care if it's a sub n or b sub n. Let's make it b sub n. Okay. So what we're going to do is we're going to find the limit of a sub n over b sub n as n goes to infinity. Well, a sub n is, what was that? Square root of n over n squared plus 1 divided by 1 over n to the 3/2. Well, complex fraction, I'm just going to bring that up here, over 1. Okay, so I've got that. So on top, I'm left with, what is that, n to the second? Ah, n to the second. On bottom, I'm left with n to the second plus 1. This is the limit as n approaches infinity. Well, if I did that, that would just be 1, wouldn't it? The limit would just be 1. So now, since it equals 1, we can conclude by the limit comparison test, because we know this is a p-series, right? This is a p-series, and this is 3/2 is greater than 1. So I know that this converges. So now, using the limit comparison test, since a sub n over b sub n is equal to 1, it says either they both converge or they both diverge. Well, since I know that this is a p-series and it converges, that means a sub n must also converge.
So,
Okay,
Mr. Shanklin,
yep.
you want to concoct the b sub n in a way that fits well with a sub n to then justify a finite number. So
What we
you,
want to do, we really want to make something similar to this.
okay.
But we want to make sure that we know, like, you want to make it into either a geometric series or a p-series. We want to make that function something that we know either converges or diverges. Like if I had a function that I didn't know if it converged or diverged, this wouldn't help me at all.
Right.
But since I made a function that is very similar to that, but I know it's a p-series and I know it converges, then it's like, okay, so now if I do the p over the, or the a sub n over b sub n, I need to know if one of them converges or diverges, because if I didn't know that, it wouldn't help me at all.
So can you usually, by just taking the highest exponent
Yes,
from the numerator and denominator?
yes, that is usually how we do it. Yep, we
Okay.
take the highest top and bottom, because this plus 1 is really not going to do much to the function, is it? I mean, really, it's the highest power on top and highest power on bottom that really affects a function. So that's really what you're looking at. And I think when we did the last problem, when we were using the convergence here, same thing. This too does not do a whole lot to this function. However, so, that's why I wrote it as 1 over 3 to the n, because now this is a geometric sequence. And I know that this geometric sequence, I know that that thing converges because my R value is 1/3, it's less than 1, converges. So really what you're trying to do is you're trying to write whatever you're trying to compare, you want to try to make sure that it's a geometric sequence or a P-series sequence, something that you know is going to converge or diverge. That is the key. And 95% of the time, it is going to be a function that you just take the highest power on top and bottom, boom, and that gives you the function that you want to use. Okay.
So one quick question. What if
Yep.
the exponent on top is higher? Wouldn't that technically cause the b sub n to diverge?
Right. Exactly. Because then it's not going right. I would agree with you.
So then you know that both diverge.
Yes. And
Gotcha.
and usually, when you look at functions like this, converging or diverging, what was the first test that we used to use? I mean, didn't we used to use that limit as n approaches? And that's why some of these functions I don't get, because it's like, why didn't we just use the limit as n approaches infinity of n to the 1/2 over n squared? Well, this is a big over a small, isn't it? Big over small. Oh, I'm sorry, small over big. And that equals 0. And then isn't the first convergence that we used, and I don't even remember what the test was called, but if it equals 0, it told us that it converged. So there's all these different types of tests out there that you use. Some of them, but the key is when you're doing these types of problems is, can you find another function that looks similar to it? And if you can, you're going to use a limit or the direct comparison test. Now, these were not in the notes for the BC Calc test. I don't know if they're going to have this on there or not, but I will tell you that this next one, the alternating series, that is one of the items that they have starred that will be on the test this year. Okay, so what is an alternating series? Well, an alternating series is pretty easy. I mean, if one term is like, if this term is -2 and this term is 4 and this term is -8 and this term is 16, this is an alternating series. It goes from negative to positive to negative to positive, or it could be positive 2, -4, positive 8, -16. These are what we call alternating series. And when you think about an alternating series, when I think about an alternating series, to me in my head, it's like, okay, you're adding negatives, you're adding positives. How does it converge or diverge? I mean, that to me it just blows my mind away. It's like I would think that it's always growing because you've got a positive and negative, negative, but it doesn't. So this is the one that will be on, well, I don't know. They can't put everything on the AP test this year. There's no way. 45 minutes is not enough time. But this is one of the items that they said will be on the test, okay? So an alternating series, so far most series that we've dealt with have had only positive terms. In this section and the next section, we will study series that contain both positive and negative terms. The simplest such series is an alternating series whose terms alternate in sign. For example, the geometric series -1 to the n, and this is what really makes it, this term right here really makes it go from positive to positive, because you've got -1 to the n. So if you found the first, this, I suppose if you put 0 in here, this is going to be 1, this is going to be positive, then it's going to be negative, then it's going to be positive, then it's going to be negative. So here are my terms. I'm going from positive, negative, so forth. Alternating series. This is an alternating series. This is an alternating geometric series with r equal to -1/2. Okay, because if you think about it, 1 times -1/2 is -1/2. -1/2 times -1/2 is +1/4. And so this is a geometric series with my r value being -1/2. So an alternating series occurs in two ways. Either the odd terms are negative or the even terms are negative. So this one, the odd terms are positive and the even terms are negative. So that's the only two ways that it can occur. And here is the rule for alternating series. If a sub n is greater than 0, the alternating series, okay, so I've got -1 to the n, a sub n, or -1 n plus 1, so that means, you know, this one would start with a positive, this one's going to start with a negative. Oh, they're starting at 1 now, so changes. When n equals 1, this will start with negative, positive, negative, positive. This will start with positive, negative, and it all depends where they start. If they start at 0, you know, then this would be a negative, positive, negative, but that really makes no difference. It says converges when the two conditions listed below are met. So the limit of a sub n is equal to 0. Okay, so that's one condition. And a sub n plus 1 is less than a sub n for all n. This part is sometimes a little hard to prove. I mean, sometimes it's easy to prove, sometimes it's hard to prove, but that's those two conditions. If those two conditions are met, then the function converges. Okay, so let's try an example. Determine the convergence or divergence of this function. All right, so now this is a sub n, isn't it? Because we don't deal with this when we're dealing with finding the limit. All we do, so a sub n is 1 over n. I'm going to find the limit as n approaches infinity of 1 over n. Well, that is 0, right? So that means, if we go back to our last slide, a sub n, as the limit as n approaches infinity of a sub n, is 0. Condition 1 is met. Okay, so now I have to find out about a sub n plus 1. So my second condition to be met says that a sub n plus 1 is less than a sub n. Okay, so, oops, I went backwards. So a sub n plus 1 is less than a sub n. Okay, so this is 1 over n plus 1 is less than 1 over n. Is that true? Okay, is that a true statement? Is 1 over n plus 1 less than 1 over n? Is that a true statement?
Yes. Do you have to count the negative less than?
No, you do not. This, when we're doing the test, this no longer is in play.
Oh, right.
It's
Okay, gotcha.
only
So
this part.
it'll
This
always
is
be
a sub n.
positive.
Okay, yep. So
Got
now I look at this and say, oh, heck yeah, this is always going to be less than, because, and I could put a few values in there. Let's put 1 in there. So this would be 1/2 is less, oops, 1/2 is less than 1. I could put 2 in there. 1/3 is less than 1/2. Yeah, I could put 3 in here. So that's 1/4 is less than 1/3. So I visually, it's like, oh yeah, this side is, the left-hand side is always less than the right-hand side. But mathematically, you should see that also, because this is always going to be greater than the denominator here. So yeah, that has to be, if the denominator is greater on this side, it has to be less than. Okay, does that make sense? So in this problem, both statements are true. So this function converges. Okay, now here's the question. If this wasn't in front, if this was not in front, does this converge? Is that a convergent series sequence?
No, because it's the harmonic series.
It's exactly right. That does not converge. This, since p is equal to 1, this is the harmonic series. It does not converge. The p-value is 1, does not converge, it diverges. That just blows my mind away. It's like, holy cow, how can 1 diverge and 1 converge? that just blows my mind away. I mean, my mind doesn't think that way, but that is, and usually I like to have problems where it's like I can see, I mean, I can do the tests. I mean, I can test to see if um, a sub n, you know, I could do these two. I can test this. I can test the limit as n approaches a sub n equals 0. I can test this. So I can test the conditions and, you know, says it converges. So I have to agree that it converges. But in my mind, that really messes me up because I know that 1 over n diverges. So that to me is one of those things that it really does not doesn't connect all the way to me. But I go along with the calc because somebody obviously had to prove that. So I'm going to go along with it. All right. I would like you guys to try this one. Okay, I've got negative 1 over n squared over n squared plus 5. I want to know if it converges or diverges. Okay, tell me if it converges or diverges.
I think it diverges because not both of the criteria are met.
Ah, now let's go back. I have to agree with you. Okay, but let's go back to our statement. Okay, the alternating series just tells us if it converges. It doesn't tell us if it diverges. Okay, so I agree with you that this function does not converge. Okay,
Oh,
condition one. 1 second, my dog is whining outside. I gotta let him in. Okay. Oh, never mind. Sorry about that. My wife is home. That's why the dog is whining. Okay. So I agree that condition one is not met because when we do a sub n is equal to n squared over n squared plus 5 as the limit of n approaches infinity, this is 1. It equals 1. That is not 0. So condition 1 is not met. So I know the function does not converge, okay? Now I cannot say it diverges. Now I would say that it probably does diverge, but we really can't say that because that's not what the rule says. The alternating series rule says that if a sub n, if the limit is if the limit as n approaches infinity of a sub n is equal to 0, and a sub n plus 1 is less than a sub n, then it converges. It doesn't tell us anything about divergent. So I would have to use another test in order to see if this thing diverges,
I
okay?
don't get it. Is there action?
No, well,
Because if it doesn't converge, how does it also not diverge? Wouldn't we know
uh,
it diverges then?
good question. It would diverge. I mean, the only problem is you can't, using the alternate series test, you can't say it diverges. Okay, the only thing you can say is it does not converge. You're using that the alternating series test to tell us if it does converge or not. It doesn't converge. We know it doesn't converge because we found that system. However, in order to prove it diverges, we have to use a different test. Now, you are absolutely right. The way I think about it is, hey, if it doesn't converge, it has to diverge, right? So, but the rules of calculus says that you can't say it diverges because of the alternating series test. You just can't say that. So you'd have to use a different test in order to prove that. Well, again, we know that if we took the limit, and now if I took the limit, you have to use the whole function then. So if I took the limit as -1 to the nth power over n squared over n squared plus 5, then if I tried to find the limit as n approaches infinity here, guess what? If you put infinity in here, does this converge or diverge? I mean, it doesn't exist, right? So this does not exist because it just keeps going -1 to 1 to -1, back and forth, back and forth. This, we know, goes to 1. So it really does diverge. And I would say, you just using the alternating series test, we could have told that before because we found one of the conditions not to work. So you are right when you say, well, there's only two things. It can either converge or diverge. So really, if you find one of those conditions not being met, you could really just right away just say it diverges. Because in the directions, it says determine if the following series converges or diverges. It doesn't say prove it diverges. So since we found that it didn't converge, it has to diverge. And I would not, I just go by what the book tells us on these things. And this is how they had it. It says so the first condition is met, or the first condition isn't met. And so there's no reason to check the second, since we know it's not convergent. In these cases where the first condition isn't met, it is usually best to use the divergent test. So here's a divergent test. So the limit diverges. Okay, that's how our book tells it to us. But I agree with you. I don't know if it was you, Caleb, or Henry that said, isn't there two possibilities? It either converges or it diverges. You're absolutely right. If you can show that it doesn't converge, we know it has to diverge. It has to. So instead of doing all that extra work, I would not do all that extra work. I would just say, hey, it's got to converge or diverge. Sorry about that. All right. How about this one? It says use the alternating series test to determine the convergence of the series. Okay, so I'm going to let you try it, see what you get. Okay. Okay, does it converge or diverge?
It diverges because a sub n plus 1 is not always less than a sub n.
A sub 1, okay. Tell me that again.
The one rule where a sub n plus 1 has to be less than a sub n. It doesn't follow that.
Okay, so we've got sine squared of n up on top, right? Over n. And a sub n plus 1, so that would be sine squared n plus 1 over n plus 1. I'm not so sure if that's true, because this, we know this is going to be between -1 and 1, right? We know that. But I don't know if the n plus 1 is going to change, because this number up here is going to change. It's not going to be the same as this. So just adding a 1 to the bottom doesn't really, I mean, if this was sine squared of n, and the top here was sine squared of n, and this was n plus 1, and this was n, that'd be easy to tell. Then I'd say, yeah, this is bigger. It's not going to work. But this is changing. These two on top are not the same. Did you understand what I'm saying? That it's not the same there?
Are you saying that it isn't true or that it is true?
I'm saying I'm not sure if it is true or not. I'm
Oh,
not.
right. Okay.
I'm not. There is no way I could prove that sine squared of n plus 1 and the n plus 1 on the bottom I'm not sure if I could prove that is true or not.
At 4, I think. So sine of 4 squared, sine of 3 squared divided by 3 is equal to 0.006 rounded, 0.007 rounded, and then sine of 4 squared divided by 4 is 0.143.
So, okay. All right. So what was this one here at 3?
Yeah.
Point.
So 0.007 is at 3, and then at 4, n equals 4,
Oops.
it's greater than. So n plus 1 is greater than n.
So that. So so are you saying condition 1 or condition 2 is met?
No, it's not met.
It's not
So
met? Okay.
it would not converge.
So diverge?
Yeah, so also I think a series doesn't have to diverge, it can just not exist. Because like you said, in a true alternating series where it's just going from 1 to -1, it neither diverges or converges.
Yeah, it's always
Be
staying at,
getting bigger.
right.
So a function cannot, a series can't exist as well. So I think that's the issue with like the alternating series, because it can just do the same thing over and over again.
Right, so it could be, okay. That's why they say that you should use a divergent, okay, that makes a whole lot more sense with the alternating series, because you're right. It could just keep going back and forth, back and forth, back and forth. Gotcha. All right. Now, there's something that's called absolute and conditional convergence. Okay? Absolute and conditional convergence. Occasionally, a series may have both positive and negative terms and not be an alternating series. For instance, the series sine of n over n squared. Well, remember, sine can go between -1 and 1, right? So we could actually get positives and negatives on top, and the bottom can always be positive. Okay, so it has both positive and negative terms, yet it is not an alternating series. One way to obtain some information about the convergence of this series is to investigate the convergence of the absolute value. Okay, so if we did the absolute value of that function, then we can say, okay, and this is where absolute convergence comes in. By direct comparison, okay, so direct comparison, they're using, and this is where it gets interesting. Remember direct comparison, we always talked about, we were talking about using the highest power on top and highest power on bottom. Well, what is the highest power on top right now? It's not a variable, is it? What is the largest sine can ever go? You're right. 1 is the largest it can ever go. So that means I could use 1 over n squared. If I'm going to do direct comparison, 1 over n squared, oh, this is a p-series, isn't it? This is a convergent p-series. So that is where we're using the limit comparison test. That's kind of cool because, you know, and this is always going to be less than this for all n greater than 1. So therefore, by the direct comparison test, the series S, the sine of n over n squared converges. The next theorem tells you that the original series also converges. And this is called the absolute convergence. If the series, the absolute value, converges, then the series A sub n also converges. That means it is an absolute convergence. So we can, right. That is exactly right. We are not finding the value of where it converges. We are just saying if it converges or not. Okay? And if we take the absolute value of the function and we can prove that that converges, then we know it converges, and some people say it converges absolutely. Okay? So that is what, when you ever see, if somebody asks you, does it converge absolutely, what you're doing is you're taking the absolute value of that. Okay, and here's the alternating harmonic series. We knew, we already did this problem, right, for the alternating harmonic series. We found that it converged, right? The alternating harmonic series converges, but we know that the harmonic series does not converge. Okay, so it converges by the alternating series, yet the harmonic series diverges. So this type of convergence is called conditional convergence. So the series a sub n is absolutely convergent when the absolute value converges. The series a sub n is conditionally convergent when a sub n converges, but the absolute value does not. Now, most of the times, they're only going to ask you if the function converges or diverges. However, a couple times they'll say, is it absolute convergent or conditional convergent? And this is all it means. The absolute convergent means that the original function converges and the absolute value of the function converges. To be conditional convergent, that means that a sub n converges, but the absolute value does not. Because if I put the absolute value symbol in here, this does not converge. This becomes a harmonic series, does not converge. So that is the difference between absolute convergence and conditional convergence. Determine whether the series -1 to the n plus 1 over 3n plus 2 is absolute convergent or conditional convergent. Okay, so what would this be? Absolute convergence or conditional convergent or divergent? Conditionally convergent. Okay, that's one guess. I disagree with that. I'm going to disagree with that answer. I'm going to do the limit I'm going to do the limit on this one. The limit is n approaches infinity of 2n plus 1 over 3n plus 1, or 3n plus 2. That gives me 2/3. It's not equal 0. This diverges, doesn't it? Doesn't this series diverge? Mm-hmm. It's a divergent series. All right. Some of this stuff can really mess with your heads. All right, that is all I have for you today. Any questions? Now remember, we do not have school on Friday. We do not have school next week, Monday. So next week, Monday, I will be, well, I don't know when I'm going to do it, but I will record the next session. The next session is the ratio test. And let me tell you, I think the ratio test is the #1 test of convergence. Once you see this test, you will not use any of these other ones. You won't, well, I suppose, I don't think the ratio test works with an alternating series, but the ratio test is amazing. It is the type of test, that's the test that you will use more often than not. I don't know why they just don't teach it right off the bat, and then all of the rest of them usually go by the wayside. You don't need them. All right, you guys have a great Easter, and I will see you back in 2 weeks.
Mr. Shanklin,
Yes.
I have a quick question. What should I do to change my incomplete grade on assessment 9C?
How did you, Henry? Is this Henry or Caleb?
This is Caleb, sorry.
Caleb, how did you get an incomplete? Was it because you didn't have your notes, or was it because you got them all wrong?
You said number 4 is a harmonic sequence, so I think I got that wrong.
Okay. Usually they're set up to take twice, right, Caleb?
Yeah, I can take it again if you'd like.
No, or you could just email me the correct answers. That's perfectly fine. You know,
Oh, okay.
if it's just 2 or 3 problems, just email me your correct answers, and I will update it.
Thank you. Sounds good. I will do that.
All right, you guys have a great week. Okay. Tomorrow's supposed to be 70 degrees. Get outside, enjoy the weather,
Yeah.
except make sure you stay away from people. 6 feet.
Thanks, Mr. Shanklin. Bye.
All right. Bye.